Welcome to this lesson on metric spaces. Today, we are going to explore a beautiful and foundational concept called the closure of a set. We will build this idea from the ground up, so do not worry if it sounds completely new to you. Let us start with a simple analogy. Imagine a piece of land that you own. You have the grassy area inside, but what about the exact boundary line where your property meets your neighbor's property? If you take your grassy area and add the exact boundary fence to it, you get the closure of your property. In mathematics, a set might be missing its edges. The closure is simply the set itself plus all of its missing boundary points. It is the process of closing the set by sealing up any gaps on its edges. Now that we have the intuition, let us look at the mathematical definition. In a metric space, where we can measure exact distances, the closure of a set is defined as the union of the set and its derived set. The derived set is just the collection of all the limit points of a set. A limit point is a point where any microscopic circle drawn around it will trap at least one point of the original set. Another way to think of the closure is that it is the tightest possible closed box you can draw around your set, containing absolutely nothing extra except the missing boundary points. This brings us to the fundamental formula for the closure of a set. The symbol A with a bar over it represents the closure of the set A. The U symbol stands for the union, which means we are combining everything together. Finally, A prime represents the derived set, which is the collection of all the limit points of A. This equation tells us that to find the closure, you simply take your original set and dump all of its limit points into it. If a point was already in A, it stays there, and if a point was hovering right on the edge, it gets added. Before we move on to any proofs, let us see this formula in action with a concrete example. We want to find the closure of the open interval from 0 to 1 in the metric space of real numbers. This open interval contains all numbers strictly greater than 0 and strictly less than 1, but it does not include the endpoints 0 or 1. Our strategy is to identify all the limit points of this set and add them to our original collection. Continuing with our example, any number inside this interval, such as 0.5, is clearly a limit point because any small bubble around it traps other numbers in the interval. Now we must examine the boundary points, 0 and 1. Even though 0 is not in the original set, any open ball drawn around it will always overlap with the inside of the interval. Therefore, 0 is a limit point, and by the exact same logic, 1 is also a limit point. So our derived set includes everything from 0 to 1, inclusive. Now we apply our fundamental formula. We mathematically combine the open interval with the closed interval of limit points. When we combine these two sets, the missing endpoints 0 and 1 are finally filled in. The final answer is the closed interval from 0 to 1. Physically, you can imagine taking a line segment that is missing its tips and gluing those tips back on. We have successfully closed the set by sealing up its missing edges. Let us look at a second, slightly more complex example. We will find the closure of the set of rational numbers in the real number line. Rational numbers are fractions, scattered everywhere, but with tiny microscopic gaps filled by irrational numbers. We need to figure out what happens if we take every rational number and add all of its limit points. Our strategy is to test an arbitrary real number and see if it qualifies as a limit point. Let us pick any real number x on the number line and draw an open ball around it with a radius r. A fundamental property of mathematics is that between any two real numbers, no matter how close they are, there is always a rational number. Because there is always a rational number in any interval, this open ball will always contain at least one point from our set. This proves that every single real number, without exception, is a limit point of the rational numbers. Since every real number is a limit point, adding the limit points to the original set gives us the entire set of real numbers. The closure of the rational numbers is the complete real number line. In mathematics, we say the rational numbers are dense in the real numbers. This means that by closing the gaps in the rational numbers, we completely fill the entire space. Now that we have successfully used the formula in two examples, let us understand a fundamental theorem. The closure of a set is always a closed set. To prove a set is closed, we must show that its complement, meaning everything completely outside of it, is an open set. Let X be our entire metric space. We will look at the points outside the closure. Let X be a point in this outside area. Because X is not in the closure, it is not in A and it is not a limit point of A either. Continuing our proof, we must rely on the precise mathematical definition of a limit point. Since we established that our chosen point X is not a limit point of the set A, there must exist some open ball that completely misses the set A. Think of this open ball as a protective, microscopic bubble of radius r drawn around the point X. This formula on the screen states that the intersection or overlap between our protective bubble and the original set A is absolutely nothing, which is represented by the empty set. This lack of overlap is the crucial logical step we need. This brings us to the final step of our proof. Since this bubble does not touch A at all, no point inside this bubble can be a limit point of A either. Therefore, the entire bubble is completely outside of the closure. Because we can draw this protective bubble around any point in the outside area without ever touching the closure, the outside area is an open set. Since its complement is open, the closure is officially proven to be a closed set. Let us visualize what we just proved. On the screen, you see a diagram summarizing our theorem. On the left, the dashed line represents a set A that is missing its boundary. On the right, the solid line represents the closure, where the boundary is safely contained. Notice the point X sitting outside the closure? The dashed circle around X is the protective open ball we used in our proof. Because this bubble never touches the solid boundary, it proves that the outside region is completely open, making the closure itself a perfectly closed set. You might be wondering, why does the closure of a set actually matter? In real-world engineering and physics, we often deal with approximations. For example, a computer can only store rational numbers because decimals must have a finite length, but physical reality operates on continuous real numbers. The concept of closure guarantees that even if we only work with a gappy set like rational numbers, we can approximate any real-world continuous value as closely as we want. It is the mathematical foundation for limits and calculus. We have covered a lot of ground today, so let us summarize the key takeaways. First, the closure of a set is simply the set combined with all of its boundary points. Second, it is the smallest closed set that completely swallows the original set. Finally, by finding the closure, we seal the set, ensuring that any sequence of points moving toward the edge will actually have a solid destination to land on. You now have a solid understanding of the closure of a set. Great job!